This will be mini lecture 11. Now that we have actually covered nodal and mesh analysis, which are the main analysis method for basic circuit. In fact, nodal is the preeminent circuit analysis method that's even used in software development when software get developed to analyze circuits. We're going to start layering some new concepts, essentially. And today we're going to focus on what's called the principle of superposition. This is actually a very fundamental engineering concept, although our use of it in Engineering 17 will be rather small, but it's an important part. I want to kind of give you a feel for what superposition is in terms of how we see problem solving. In many respects, when we think of superposition, we're looking at solving a circuit piecemeal, or we're looking at solving a problem piecemeal. What I tell students in general in class, say your computer is not, you get up and your computer is not working, okay? It's not turning on, or it's turning on with a blue screen. What are the kind of problem shooting things you do? Probably rebooting your computer would be one. At times you may look at, okay, what is the software that I install last that might be corrupting things? Am I plugging a new printer or some new accessories that causing the computer to face difficulty? When you do this, what you are essentially trying to do, you're trying to narrow where the problem is so that you can put your arm around it. So in essence, it is a way to focus on where the problem area is. And then you try perhaps to think you might find a solution. Is it a virus? Is it something like that? Superposition is the quintessential approach to doing this. In essence, what superposition tells us, if you have a complicated problem, can we solve the problem piecemeal and add the subset solutions together to get the final solution? Okay, so we're gonna look at it, how that applies to circuit analysis today. What I don't want you to think, essentially, I don't want you to think every time I give you a circuit going forward, you need to apply superposition. Think carefully. Only when I ask you to apply superposition, you should be very careful at applying, because it could actually multiply your work when it's applying the wrong way. So let's look at what superposition is. So in order for us to think of superposition, we have to somewhat discuss the principle of linearity. I'm actually going to go to the computer. I'm going to go to my document camera and talk about linearity with you in a different context to try to provide a little bit of insight here. So let me go to the document camera. So if I give you a function, let's say f of x, and say the function is 6x squared minus 4x. And then I ask you, so I'm going to arc back to your calculus course here. I ask you to calculate the derivative of x with respect to x. I ask you to calculate the derivative of the function with respect to x. Most of you would tell me the derivative is 12x minus 4, right? What I want to bring to your attention is, how do you actually go from this to getting the derivative to be 12x minus 4? And what you actually do, you actually do this. The derivative of x of f with respect to x is 6 times the derivative of x squared with respect to x minus 4 times the derivative of x with respect to x. Okay? And that's how you get to this. So you are able to do this because the derivative operator is what's called a linear operator. In essence, I'm able to essentially consider the function as the sum of two functions. That's the first thing. So I can do the derivative of one function. And my document camera froze. So again, I can get to this derivative 12x minus 4 by looking at the original function as the sum of two functions. One function 6x squared, and then another function minus 4x. So, and then what I do next is essentially I differentiate the 6x squared. That's what gives me the 12x. And then I also differentiate the minus 4x, and then I can add those two pieces to give me the complete solution for the derivative of that combo function. The other property that I use is called the scalar property. And you can see that very well in both sides here. Let's say I want to differentiate the minus 4x. What I do, in effect, I differentiate x with respect to x, which gives me 1, and I multiply it by the constant. These are essentially requirements that define the linearity of the derivative. And you have the same requirement if we were to do an integral, and an integral of some of the functions, we would have the same thing. So I'm going to go back now and talk to it in terms of circuit analysis and Ohm's law. So to understand superposition, we have to understand the concept of linearity. I just showed you, in a way, linearity for derivatives, and you can ensure that you can do the same thing for an integral. But let's look at a function. Let's look at a circuit that has a current source, putting some current I1 into a resistor R. And then I ask you, what is that voltage across the resistor R? Of course, Ohm's law, the passive sign convention is satisfied here. I would basically say the voltage across the resistor is simply the resistance times the current, because that's a fairly obvious thing. Okay, if I have a different current, I put a current I2 into the resistor, then you can also assume, you can also think that the voltage will be the new current I2, again, would satisfy the passive sign convention here, times the resistance, that gives me the new voltage V2. Okay, now, if I add these two currents, if I put a current that has the two previous current I1 and I2 value into that resistor, what do we get? We get, of course, R times I1 plus R times I2. So we get the sum of these individual voltages. And that should remind you of the example that I did with the derivatives, in terms that I had the two function and I did the derivative of the first plus the derivative of the second, and then we add together. So this is a major rule in terms of linearity. If the input is the sum of two functions, then the output is the sum of the responses, the individual responses to these individual functions. That's law number one of linearity. If you put an input that's the sum of two functions, you get the output that's the sum of the original two responses from these individual functions. Law number one. Law number two is the law that we just saw about the constant. If now, instead of putting a current I1, I put a constant C times I1. So what do we get here? Again, I can apply Ohm's law, and I say the voltage across that resistor is R times C times I1. So it's C times the original functions. So the input scale by a constant gives you the original response scaled by that same constant. That is law number two. So we say that with these two laws satisfied, the voltage current relationship for the resistor is a linear relationship. So that's, in fact, in many places in this country, this particular course is called linear circuit analysis. The only exception we're going to have in this course is operational amplifiers, when we cover for about a week worth of lecture. But basically, the elements, what we're going to cover in this particular course, are linear circuit elements. So we will define a linear circuit element as one that has a linear voltage current relationship. The resistor is one such element. Okay. All right. These are the requirements for superposition to apply. So a linear circuit, so we define a linear element is one that have a voltage current relationship that is linear. A linear circuit is comprised of independent sources, linear dependent sources, and linear elements. Of course, the only elements we have besides sources thus far in the course are resistors, which is clearly a linear element. I was just essentially showing you that case. Why do we talk about linear dependent sources? Linear dependent sources are either voltage or current types that have essentially these types of relationship: constant multiplied by current, addition, subtraction, constant multiplication. Anything that has multiplication of function or squares is not linear. So the bottom two are non-linear dependent sources. The top two are linear dependent sources. In this course, we are only concerned with linear dependent sources. Okay, so I want to show you some example of that. So superposition, I am essentially going to, this is tell you kind of the letter of the law, but I will also give you a feel for it. What superposition says, if you have a circuit with, say, 3 independent sources, current or voltage type, you're going to solve the circuit 3 times, each time with one of the independent sources alone, and then calculating a subset of the response. And as you do it 3 times, then you add those subset responses, and then that's going to give you the original response that you were seeking. So this is actually the formal. It says, given the linear circuit with n independent sources, let Y be either the voltage or the current through an element, be the response you're seeking. Then Y is equal to Y1, Y2, Y3, up to sub Y sub n, where each of these subset responses is the response with the correct source on and every other source turned off. Now, this looks very obviously very confusing. Let's do a circuit example so that we can actually ground this. Again, the one thing I want to point out here, don't ever turn off dependent sources. So superposition only operates on independent sources. The next thing that you want to know, what happened to a voltage source when you turn it off? The voltage source turning off is, we can represent that as a short circuit. The way I tell students to remember this, if you turn off a voltage source, you want it to be 0 volt. So the way we represent 0 volt is essentially a wire. Okay. So when we turn off a voltage source, we're going to replace it with a wire. Similarly, when we turn off a current source, we want the current to be 0. How do we get current to be 0? We're going to replace the current source with a broken wire. So these 2 things are important because that's superposition function on turning off independent sources one at a time. So let's look at an example to see how that plays out. So again, I'm specifically asking you to use superposition here to calculate the voltage V across the 2 ohms. So the first thing when you think of superposition, how many independent sources we have? And in this particular case, we have 3. So the idea essentially is that I'm going to solve this circuit 3 times. Each time that I solve the circuit, I'm going to have one of these independent sources on, and I'm going to turn off the other. So the first one might be the 10 volt alone, turning off the 2 amp and turning off the 4 amp. And then the second circuit will be the 2 amp alone, turning off the 10 volt, turning off the 4 amp. And the third circuit will be the 4 amp alone with the other 2 turned off. Of course, you have to understand, or you have to know what happened when you turn off a voltage source, what happened when you turn off a current source. And we talked about in the previous slide, when we turn off a voltage source, we're going to replace it by a wire. When we turn off a current source, we're going to replace it by a broken wire to make sure that the current is 0 between those 2 leads. Okay, so we'll solve this circuit. It is asking you to use superposition, or it's saying essentially solving it for one source, one independent source at a time, and then add the response at the end. So let's look at the first circuit here. So the first circuit here, again, I'm going to turn off the 2 amps, and I'm going to turn off the 4 amps. And when I turn off the 4 amps, I'm replacing these current sources by broken wires. That's what I'm showing you here. This is where the 2 current sources were, right here and right here. So this circuit is a circuit with only 10 volt, and I'm replacing this original voltage by VA because that's not equal to the original voltage. It's going to be a subset. So you're going to have VA, VB for the next circuit, VC, and then I'm going to add these three to get the original solution. Of course, when we think of superposition here, that implies that these individual circuits are simpler than the original circuit to solve them, much simpler. This is why I caution students to not use superposition willy-nilly, because often you could multiply your work by 3 times in this particular case. Okay, but I'm using this example just to show you how superposition is applied to circuit analysis here. So how you solve this circuit, pretty up to you. You can use mesh, nodal, probably even current voltage division, since you don't even have to use the full method. I could actually realize that given the 3 ohm and the 1 ohm are in series, and then put that in parallel with the 4 ohm. So we could do just about any method of solutions that we have. Okay, that's not as important right now. All right. So here, for example, what I'm going to do here, just to make the problem simpler, I can realize that these two are in series. And the combination is in parallel to the 4 ohms. So I end up getting 4 ohms in parallel with 4 ohms. That gave me 2 ohms. And then I can easily apply voltage division to get VA after that. So this is the combination. Okay. The 4 ohms in combination with the 1 and the 3. And then from there, I can use voltage division to go from the 10 volt to the VA. So VA is going to be 10 divided by 2 plus 2 multiplied by 2. So fairly simple. Generally speaking, you would need to do mesh or nodal on the sub-circuits. This is a particular case where you can do something rather simple to solve this particular sub-circuit. But that's VA. That's with the 10 volt source alone in the circuit. Then we go ahead and go back to the original circuit. And this is where the voltage, the 10 volt was. So you can see I replaced the 10 volt by a wire to make the voltage go to 0. And then I still have the current source was here. That's broken wire for that current source that was on top. So I'm going to now resolve this circuit, and I have the response to be VB. So that's going to be my second response here. Okay. Here again, you can look at things. I can see that the 4 ohms is in parallel with the 2 ohms. So we can, again, we could do mesh and nodal. Okay. But I can see that the 4 ohms and the 2 ohms are in parallel. So I could combine that in parallel. And then once I get that, I can calculate I2, then I can calculate IB. Honestly, at this point, I would recommend either doing mesh or nodal. It gets a little bit easier than actually doing this kind of combination of resistors. But I can combine the 4 and the 2 ohm in parallel. You can see in orange here, because they share both nodes. They share this node, and they share that node, okay? And if I do that, I get this. I get the 8.6 ohm, okay? I haven't lost VB because it's a parallel combination. I did lose IB, but I haven't lost VB, okay? But I now can use current division fairly easily to calculate the current I2. And again, the method that I'm using is not that important. You could actually use mesh and nodal, but you can see that it could pretty much get complicated if you're not careful at using superposition. So here, I'm going to use current division. I can combine the 1 and the 8.6, and then use current division to get I2. Okay. So I combine the 1 and the 8.6 in series right there. And then now I'm ready to use current division. So current division is going to give -2 because the current, I need the current that's coming out this way, and then drops down to the 14.6 resistor. Okay, so I2 is equal to -1.125. Once I have I2, I can go back and then reapply current division right here. I can reapply current division, okay? Because because the 2 ohm and the 4 ohms, essentially, they are in parallel. And then I get IB to be -0.75. And once I get IB, I can have VB. Again, it's a roundabout way. You would have been perhaps better off and easier to do a full-on nodal or mesh in this particular problem. But I just wanted to show you a little bit of a different approach here. Okay. Finally, the third circuit is the one with the 4 amp alone And again, this is where you had the current source here, and this is where you had the voltage source replaced by the wire, the current source replaced by an open circuit. Two broken leads. And at this point, again, we could combine resistors. The 2 ohms and the 4 ohms are still in parallel, so I could combine them. We could use we could use node analysis or mesh analysis as well. But if I combine them, I get this. Okay. That's the 4 ohm and the 2 ohm in parallel. Okay. Then I can use current division and get IC fairly readily by combining the 3 ohms and the 8.6 in series. Okay. So that's what we get. And I can get VC once I have IC. VC is equal to 1 volt. What superposition tells us is essentially tells us that the original voltage for the circuit that was provided is a sum of these individual response. Each response is with one independent sources, with the other ones being turned off. So in this particular case, V is equal to VA plus VB plus VC. So the premise of superposition essentially assumes that these sub-circuits are a lot easier to solve. Honestly, the circuit that I'm using is not so evident to me that I would use superposition. So I'm using it as an example because it had 3 sources, and I wanted to show you how that plays out when you have several independent sources in this particular case. And I hope that makes sense. So the second example that I have, although I'm not that inclined to spend a lot of time in it, I put this example out to show you how superposition works when you have a dependent source. You have that dependent source 7IA. Remember, superposition only works with independent sources. You never turn off dependent sources. This is just a reminder of that to you. This problem is asking to use superposition to find the power absorbed by the 1 ohm. This 1 ohm here. Okay, so what superposition essentially is saying, I'm going to solve 2 circuits, one with the 4 amp on the left alone, and one with the 2 volt on the right alone, and turning off the other. The dependent source never gets turned off and it stays in the circuit. You have to remember that dependent sources are used to model electronic devices. They're not real sources. Okay, so when we use superposition here, we're going to look at 2 sub-circuits. The first one here, so this is where you had the voltage source. I turn off the voltage source and replace it by a wire, by a short. So we would solve this particular problem with the current source alone. And I relabel the current that I'm seeking here. So I'm seeking the current IT, because once I have the current essentially on the 1 ohm resistor, I can actually calculate the power. So I relabel that current to IT. Okay. So we could solve this thing in any way you want. Again, we could combine, we could do mesh node. All that's not that that's not that important here. I'm going to do a mesh. So there are 3 meshes. This is my source equation for that current source on the left, the 4 amp current source. The current I1 is simply 4 amp. And then I write 2 KVL equations, one in mesh I2 and one in mesh I3. Okay. Nothing specifically about that. This is just to remind you, you don't touch the dependent, so you never turn off a dependent source when you apply superposition. Same thing for mesh I3. Okay. All right. And then we go ahead and do Ohm's law for all the resistors. Put the Ohm's law into the 2 KVL. No KVL in mesh I1 because there is a current source. We put that and then we get, essentially, we solve, and we get our mesh currents. And IT is minus 1.6. So that's the first sub-circuit with the current source on the left alone, having turned off the voltage source here that was on the right. Okay, that was right here. The next circuit, what we would do, we would look at the 2 volt. And again, you see the current source is replaced by an open circuit, so it disappears. And I can basically do mesh again, except I don't have the current source that was on the left. So I'm going to write 2 KVL equation here. I relabel the current on the 1 ohm as IL because it's a different circuit. So we go here, and do two KVL equations, one in mesh I1, one in mesh I2. Okay, so that's circuit number 2. Notice again, we don't touch the dependent source. It is there. Okay, so Ohm's law, just like we normally do, we put them in, we solve for the mesh currents, and we get IL. IL is simply minus I1, so we get IL. So the complete problem for this is the subcurrent IK, the original current under 1 ohm, is essentially IT plus IL. That's what superposition tells us. And once I have that, I can calculate the power for the 1 ohm resistor. So this is just an example to show you how superposition function only on independent sources. We don't touch the dependent sources because they're really modeled for electronic devices. So two things we need to know here. We need to turn off, if we're using superposition, we turn off one independent source. We turn on all independent sources except one. So we do one at a time. The other thing that I want you to know, what happened to a current source when you turn it off and what happened to a voltage source when you turn it off. If we turn off a current source, we want the current to be 0. And the way we show that is by having broken wires. If you turn off a voltage source, we want the voltage to be 0. And the way we model that is by putting essentially a wire, because that enforces the voltage to be 0. And we never touch dependent sources. They're basically, they're always in the circuit. That concludes our lecture on superposition.